Hello everyone, thank you so much for joining us today. My name is Sarmad Mehrdad and I'm a master's degree student here in Clarkson University in mechanical engineering. And today I want to talk to you guys about Clarkson University's Open Manipulator project. So without further ado, let's start. Needless to say, you first have to log into your ROSDev Studio account so that you can have this ROSdev opened to gain access to different files that are going to be mentioned during the course of this presentation. So let's go to the Tools tab and open Jupyter Notebook. All right, so let's go to Open Manipulator first. Okay, so first let's have an overview. First we're going to talk about how we built this robot, the design of it, the physical design, and then the simulation of it. We're going to talk more in depth about the controls. After that, we're going to talk about the simulations in Gazebo and RViz along with MoveIt. And after that, we're going to take a look at how we can interact with the real robot through ROSDev Studio, for getting the same functionality that you see in simulations part. And for the final act, we're going to see how this robot can play tic-tac-toe. So let's introduce the robot first, and I have the live feed of the robot itself here. Okay, and I'm going to switch back to the camera reading a lot during this presentation so that you can have a better understanding of how this robot is built. Okay, so our robot is a 7 degree of freedom serially linked robot, and it's going to play tic-tac-toe for you eventually. We're going to demo that. Let me show you the camera again. You can see 7 degrees of freedom here, 6 of which are used for the movement of the robot itself, and the 7th one is for the gripper at the end of it. Now the gripper is something very essential here, and we're going to talk more about how it's designed. I hope you can see this. Okay, this is how the gripper is made. There are 2 fingers here, and they are connected through this link, this curved link that you see here, to the 7th motor, which is this one. There's a 1010 bar, 10 millimeter by 10 millimeter for the cross section, aluminum bar that goes through them. Okay, now the motors are Dynamixel motors. Talk a bit about them. Dynamixel motors are made by Robotics company, and we are using 2 different models of them for this robot. We first initially tried to use only one type of these Dynamixels for the entirety of the robot. Then we realized we can switch 2 of them with a more powerful version of Dynamixels, because joint number 2 and joint number 3 go through a lot of torque, and they have to have enough power to bear that amount of torque. The rest of the robot that you just saw are made by us, minus the 1010 bar, obviously, and the robots. They are all 3D printed, either with PLA or nylon. PLA is polylactic acid, and it's a more brittle kind of material. And nylon we use actually for the ductility of it, so that we can prevent catastrophic events like breaking parts or links. If I show you the camera again, this part here that you see the robot is being fitted in. This is the 2nd joint, by the way. The first joint is on this bench and is responsible for rotating the base of it. Okay. This part is from nylon, and the gripper fingers are also from nylon. The rest all PLA. And we removed some shells so that you can have a better understanding of the measurements and the architecture of the Dynamixel motors. These 2 motors that you see here, one here, joint number 2 and joint number 3, are the stronger ones, and the rest are a bit weaker. And you can see the dimensions of them. Okay, we talked about the gripper. let's talk about the simulation now. All the parts that are 3D printed first were designed in the SolidWorks CAD package. After doing that, we assembled the robot as is physically in the SolidWorks, and using SW, short for SolidWorks, 2URDF plugin, we got our first score of the URDF model to be used in RViz and other applications. Then we had to manually alter some of the links and joints relations, especially for the gripper, so that we can be able to use them in RViz. Because the robot, as you saw, is not acceptable by the URDF, and we're going to talk about that right now. Okay, let's go back to the actual one. For the fingers, I want your attention here. This is a link. These two are links, and from one link to another, you should have one joint connecting them. But for this certain design, for us to be able to ensure that these grippers are moving along the axis of the bar, we had to first connect the bottom of them to the 7th motor so that we can able to move them by the movement of this motor. And we had to make this bar go through both of them so that we can ensure we are eliminating any rotation on the fingers so that they are gripping as we want them to grip. Now, this design makes these two links have two joints, and that is not acceptable by the logic and standard behind the URDF modeling. That's why we had to simplify this design. As we're going to see later on, we had to get rid of these two links for the model in the RViz, and for the movement of these two fingers, we had to mimic the rotation of the 7th motor with a linear simplification so that we can have a function in the simulation world as close as possible to the physical function. Now we're going to see what that means a bit later. For now, just know that this is what we had to modify. For powering up the robot, we were using a 12-volt power adapter, as you can see here, and the robot should be connected to this converter, Dynamixel to USB. One thing worth noting here is that the benefit of using Dynamixel motors, along with the feedback for the position and velocity that feedback control for the position and velocity that they provide, is the fact that you can serially connect them, or daisy chain them, as some call it, and then connect the final one to this converter, then to be connected to the USB, and have control over all of them, instead of having to connect each one to a base and then have control over them. So this is one of the very important benefits for us for using the Dynamixels. And right here, these are the wires coming out of the first robot, and they are serially connected. The last one here, we put the power here, 12-volt power adapter here. We're going to power it on later on. And the last one will go through the Dynamixel to USB converter. It connects to the USB, and this USB is connected to the computer that I'm using for controlling this and recording this presentation. And now that I'm showing you this feed, this is the tic-tac-toe board that we're using. It's a 3x3 grid printed by PLA, and this is the tray for the game pieces that the robot is going to use. And these are just for the human that is playing against the robot. The red ones are for me, blue ones are for this manipulator right here. Okay. I think we're good to go to the next level right now. Let's talk a bit about the controls of the robot. Okay. Now, controlling the robot is a very critical section that I have to be able to explain as much as I can so that we can go through the next parts easily. It's going to be a bit more confusing if I just talk through the text, so I had created this schematic view of the robot's controls, this block diagram, and if we try to go over this, I think it would be more beneficial for us to understand it better. In this section, we're going to take a look at what happens to an input signal. What is the raw input that we are giving this robot, and what happens to that signal so that eventually we can see the robot move to wherever we want it to. So let's talk about the first input first. Desired position and orientation is going to be what we are giving this robot. Desired position and orientation of the end effector, or the gripper, is what we're looking for here. So basically we are telling the robot, okay, have this gripper to be in this X, Y, and Z in the Cartesian space, X, Y, and Z in Cartesian space, and have this roll, pitch, and yaw. But we are not giving it RPY for roll, pitch, and yaw. We are giving it XYZW for quaternion interpretation of that roll, pitch, yaw. So this is going to be the input. And for those of you who are more experienced in ROS in general, you might notice that this type of messaging is categorized under geometry messages with the name pose. So by giving it an input, we are giving it a pose. And that pose is for the gripper. And this pose will get fed into move group commander block. And this move group commander block also loads in the robot's description, and by that I mean the model, and sends all of those information into the next block, which is the kinematic solver. Okay. This blue rectangle here represents the MoveIt package that we are using here for moving the robot, and kinematic solver is a very essential block in the MoveIt. Now, what does this block do? It takes two things into effect. One is the current state of the robot that it's going to start moving from, and the goal position and orientation that it wants to get to eventually. Having these two pieces of information in hand, it calculates different motor states. From now on, I'm going to call motors joints, so motor states will become joint states. What joint states should the robot attain as it goes through this path that should lead to the goal that we desired? This is what kinematic solver will calculate for us, and it generates some sets of joint states for the robot to go from one to another in order to reach that goal. That's what it does, basically. Then those sets of desired joint states, I mean, this is desired joint state, this is the eventual desired joint states, along with some sets to get to the desired joint states. All of those sets will get fed into the motion planner. Now, this is where it gets a bit detailed, and if you're more experienced in ROS, you're not going to have any problem understanding this. But this motion planner is going to act as an action client. And this action client obviously should have an action server, which is the trajectory server, and we're going to talk about that. I don't want to confuse you anymore right now. Those sets will get fed into the motion planner. And this motion planner will send those goals and act as if each one of those sets are short-term goals in order to get to the long-term goal. And one by one, it sends those sets, those joint states, to the trajectory server, and they then to be used to be fed into another block so that we can see the movement in the robot. But here is the problem. Here's when the problem emerges for us, at least. The number of joint state sets that kinematic solver generates after calculation is not enough for us to see a smooth movement in the robot. So if we don't do anything about this, the robot's movement is going to be intermittent or choppy, and it's not going to be very reliable if we are handling something. If we are gripping something that should be handled with care, that type of movement is not desirable at all. So we had to solve this problem by coding another block here named planning adapter. So what are we doing here in the planning adapter after the motion planner? Remember, we had different sets of joint states coming out of kinematic solver going into motion planner, and instead of using those sets and feeding them to the action server, we are first feeding them all into the planning adapter. What are we doing here? We are taking one set and the one after it, and we just fit a curve, a third-degree curve, between these two sets. And when I say set, it has 7 different joints. So this is like an array of joint state. No need to confuse you any further. Now, this planning adapter takes one set, the other one after it, and fits a curve. Then takes the next one and the next one after that and fits another curve. By doing this, eventually, between the first current state of the robot and the goal joint state, we are going to get a continuous function of joint states versus time. And by having that, we can read with any frequency that we desire, in this case 100 Hertz, from that continuous function. And then we are going to take those newly read sets and feed them back to the motion planner, then to be used for calling the action server. So if we want to take a closer look here, this is just for our attempt to get the message across. This is not really accurate. I'm going to explain why. So let's say this kinematic solver had generated n different sets of joint states for us. Fit all of them into the motion planner. We are going to feed the very same sets into the planning adapter. We're going to get a continuous function over time here, and then we're going to read from that function that we got eventually. Excuse me. And we're going to feed back m number of points. And m is a lot more than n in this context. Just for the explanation purposes, we wrote continuous function here, but it's not as accurate. I just wanted to let this be known. Okay, so this motion planner gives n points, receives m points, and now if we use those m number of points and feed them to the action server, then to see how it moves the robot is going to move in a very desirable, smoother fashion. Now, the trajectory server. This trajectory server, again, it's the action server for the movement, and these 5 arrows that you see are the 5 main signals that is being used between for communication between a client and a server. I mean, the action client and an action server. Namely, they named result, status, feedback. I always forget them. Yeah, goal, feedback, result, cancel, and status. I apologize for that. Okay, so trajectory server is nothing fancy. It's just a server that gets those goals and provides its service, basically. How is it going to do that? It's going to send motor commands or joint commands into the position controller. Now, right here, we can add the gripper commander block so that we can have control over the gripper as well. And this is nothing very fancy. This is nothing really complicated. It just generates a topic named gripper commander, and we are gonna publish into it by just a simple string like grip on or grip off, and that's gonna change the functionality of the gripper for us. And that gets added up to the join states and eventually gets to be the input for the position controller. Now, the position controller is where we use all those Dynamixel SDKs and codes written by the Robotics company. In this block, we are defining Dynamixel instances through their codes so that we can be able to communicate with the motors directly, sending goals to it and reading their feedback. So right here, as you see, the goal joint states go in, and you can see the movement in the robot. We are reading the current joint status over here as well, and this could have another arrow going up as for the feedback later to be used as the feedback signal between action server and action client. But we just try to simplify this region just to give you the idea of how everything here works. So, and for the position controller, we are loading also the PID gains for all the motors. The seventh one is for the gripper. Again, it shouldn't be something very complicated. We just wanted to grip something or let go of something. But the rest, I'm not going to say it's the best tuning that we came up with, but it does a decent job, so we just went with it. I don't think I missed something here. Oh, let me talk about the gripping too. For the gripper, as you see in a few moments when I'm trying to demonstrate how it plays tic-tac-toe, the gripper is going to be a bit more intelligent on how it grips something. And by that I mean it won't try to break itself and when it grips something. It has a safety measure implemented in it. And how are we doing that? We are constantly checking the torque generated by the seventh motor, or the motor for the gripper, and keep that in mind that we had set a goal for the seventh joint for it to start gripping. And if I show you here, when the seventh joint operates for the gripping function, these two fingers tend to go really close if there is nothing to grip. But if we want to grip something like this piece, we shouldn't try to go all the way in again. Otherwise, we're going to break something. So how this works is that we are sending it a goal, an angle goal for this motor, and we are constantly checking if the torque is going to get past a threshold or not. If it did, we are going to change the goal to its current state. So these two fingers are getting closer and closer, trying to get to an eventual goal. But when they grip something, when they grip something and the torque that is being generated by the motor exceeds a limit, we are going to change that goal that we have given it initially to its current state. Meaning that when the threshold gets passed, we are going to stop there. The fingers are going to stop there. And that is a firm grip. So far it served as a good grip for us. So this is how we control the gripper as well. Okay. Now we can move to the next section. I know I have bored you enough. Let's talk about the simulation now. I think I covered pretty much everything. Okay, so let's do something more practical. Simulation instructions. You don't need to necessarily have the robot connected to the computer now because we are just talking about the simulation of it. We are not going to interact with the robot in this part. Okay, enough chit chat. Let's go to Simulations tab and click on From My Workspace. In the Launch File tab, click on Clarkson Open Manipulator Gazebo.launch and click Launch. Sometimes it won't work, sometimes you'll have to just close it and reopen it. Sometimes you might even have to reload the ROSDev. While it loads, let me explain further what we're going to do. We're going to see this model load up. And I want to mention that this robots model that we are using for the Gazebo is I want to say initial, one of the initial models that we came up with for the robot. As you can see, it's not really as presentable as the robot is itself. But the robot that the model that we're using for the next part is going to be much more like the actual one that you saw here. You can spot the difference in multiple parts of this model. The design of the fingers, for example, not having those shells and skins around it. So yeah, this is what we're going to see. And then later on, we're going to use the MoveIt to move it, obviously. Okay, so let's just try reopening the ROSDev. I apologize for this inconvenience. There might be something wrong because I'm getting this error. I'm able to connect to Bossmaster. And that is strange right now. Let me reload again. I think I know what the problem was. Yes, the robot was connected. My robot here was trying to connect to the Gazebo environment here, and the Gazebo couldn't spot a master and in my local machine. So this is what happens when you try to have both worlds. So let's not do that. I again apologize for this. Now here, in this model, we had done the same thing. I'm having the hardest time. Okay. As you can see, there are no links connecting these two fingers to the 7th joint. And this is the model that we wanted to use for both Gazebo and RViz. That's why we wanted to have a model that works for both applications. That is why we made the fingers to be fixed. So you won't see any movement here for the fingers. But the robot is actually really good and functional. So for seeing that function, we're going to open a shell file. We're going to launch this launch file using this command. Okay. We're going to see the log files, everything loads up. Very good. Whenever you try to use MoveIt for planning movement here, excuse me, Manipulator or any other robot, when you see you can start planning now, that is your cue. You are good to go. So go ahead, click on Tools tab and open Graphical Tools. This is how we're going to check out RViz and MoveIt. Click on Resize to open tab. Okay, this is the robot as seen in Gazebo. Exactly, with the same joint states. So this is how the movement of the robot is going to be achieved. So right here, this entire window is for RViz, and this right here, this motion planning, this whole thing down here on the bottom left corner is the MoveIt plugin. So we're going to click on planning. This query part, I'm going to select start state and put it to current and update. And we're going to select goal state and give it a random joint state for the goal. Yeah, good enough. So by updating these two tabs that I just did, I am giving Kinematic Solver all it needs to calculate the path and then start planning it later on using other blocks. So then I click on plan, and right now I know this is how my robot is going to move if I send the command to it. So everything will get calculated before sending the function in. So what I'm going to do now, I'm going to click on execute. I'm going to move so fast to the Gazebo so that you won't miss the movement there. So ready? Here we go. Execute. Gazebo. We see the same path here. Let's do it one more time. Current. We are going to always use current for the start state because that is the position that the robot's going to start moving from. We're going to give it another update, something more reasonable. Okay. Plan. How to move. Perfect. A lot of maneuver there. Okay. Execute. Great. Now for the modeling the robot in the Gazebo, it has more to it than just modeling in the URDF version. It is the same. You should use the same environment, same syntax of the URDF. But for you to be able to see those exact movements in Gazebo, you have to use Gazebo's certain plugins for controlling the joints here. They are called ROS Control Gazebo plugin, if I'm not wrong. And by implementing those for each joint, you can read the joint states topic and assign different publishings in that topic to different joints here. So that is how you are going to get the movement in Gazebo. And by the way, this Kinect has nothing to do with it. This project, I forgot to mention in the beginning, is an ongoing project. It's not the finished score here. So probably anything that comes to your mind about the possible research opportunities for this, we are probably working on it. We are trying to add a Kinect so that we can have a better understanding of the robot itself and different functionalities like playing the tic-tac-toe, like understanding the board, We are trying to add a camera on top of the gripper so that we can have a better understanding on what we grip. We are trying to implement AI into the logic behind a movement of the robot so that it can play the tic-tac-toe all by itself without having a human in the loop as an operator, and so on and so on. So, yes, I hope that explains why we have a Kinect on the model here. So, yeah, but we're not using this. Okay, now I think I had explained everything for the simulation part of things. Yes, we saw everything here. Now we are going to connect the robot to the computer and try interacting with it. Open Manipulator 2. Okay. Now, before getting into stuff, I want to mention that we have used Python and C++ for coding this robot. And C++ is more used for the parts of the code that are mostly in depth and closer to the motors instead of the human running the robot. And the Python and C++ is used for those purposes because it's faster. And Python, we use it for like logics behind sending signals. For example, playing the tic-tac-toe. You don't need blinding speed for getting from one signal of gripping and going up and then going somewhere else. You don't need to send those signals as fast as you can, because the moment you send it, it doesn't have anything else to do with the signal that you just sent. It will be taken care of by the C++ codes more in depth. So yeah, I wanted to let you know that we are using both Python and C++ here. Now, for using the ROSDev, you obviously know that you have to use the link to add this ROSDev to your ROS Development Studio. And for adding the robot, first we're going to go, well, obviously I've done these procedures, but for you to be able to do this, you have to go to this Bitbucket link and clone this repository somewhere in your local machine and follow the instructions. It's very easy, it takes like a couple of minutes. After doing that, you can have access to localhost 3000 for adding your robot to this environment. Now, this is what you are going to see. And I have pulled it up here. This here is the device's name. I put Open Manipulator here. You can use anything you want. It doesn't really matter as long as you use the same name in your ROS Development Studio. So I am putting Open Manipulator here, and I'm going to turn on. It generates a URL for me. I'm going to copy this. I'm going to go to Development Studio. What do I have open? Let's close everything. Okay. And we are going to go to Real Robot tab, Connect to Robot. Right, ask for the robot's name. We're going to put Open Manipulator. We're going to copy or paste the link, and click Connect. It doesn't matter if the robot is actually connected through the USB or not. It's just going to do the preliminary means. It's going to go over those means for you to be able to connect the robot if you ever connect it that way. Okay, now that I have done that, let's go over the robot now. Let me show you what we're going to do now. Okay, so as mentioned before, these are serially linked. This is the converter, and this USB is directly connected to my computer over here. So I'm going to connect this. Light come on. And this is a jack for a 12-volt power, and power the robot like this. Okay, I think we're good to go. Stay. Okay. Now let's go over um, the commands that we have to run in the local machine first. Since we are using the USB for communicating with the robot, we are going to first give the read-write permissions to the USB by running this command. So let me copy this and open a terminal. Okay. Okay. Now we have given USB 0 the permission. And now we are going to run this launch file. Basically what it does is, get a glimpse of the name of it, controller launch is the name of the launch file, and open manipulator core is the package. So what it does, remember the schematic block diagram that I've shown you? It loads that entire diagram up and ready for you to use it. So after you do this, you're going to see the joint states topic show up. You're going to see the gripper commander topic for opening and closing the gripper. You're going to see 5 different signals indicating that there is an action active for you to use, and that's pretty much what it does. Now, when I run this, it goes through all the motors and identifies them, and after identifying them, it enables the torque in them. If I show you the robot right now, if I hold this up and let it go, it's just dead. It cannot hold anything, cannot hold any positions. But if I run that launch file, we can do this like this. It will go through all the motors, identifies them, and enables the torque. That's why if you hold it in a certain position, like joint state, like this, something very peculiar. Okay, if you hold it up like this and run the launch file, now we can let it go. Okay. Now we can go back to ROSDev Studio. Let's check if the robot is actually really connected. What we claim is true. Okay, let me open up another terminal. So this is my terminal in my local machine. This is ROSDev. If I get a ROS topic list, oh, sorry. Okay, you will see 5 different signals indicating an action is available for using. Gripper commander, joint states, position controller, and for 2 different states, dynamic slow state and position command, and ROS out. And let me get an echo on the joint state topic, for example. See what we're getting. Let's just get 1 echo. Okay, IDs 1 through 7, positions, velocity should be 0 because we're not moving the robot at all. And the effort, you can see the effort on joint number 2 and 3. Relatively, they're really high. That's why we had to substitute the motors with more powerful ones. Now, let's go back to ROSDev and do a list here. Yes, this means this right here that we are fully connected to the robot in the real world through ROSDev, and we can start interacting with it. So let's try pulling up the RViz with MoveIt. Now, just a quick heads up, my ping has increased drastically today from 4 or 8 milliseconds to like 40. And that might be a bit problematic. So if push comes to shove, we have to restart it or reset it using the RViz. But don't worry, we're going to get through it. I'm just telling you this so that you won't be surprised. And we can save time as much as possible. So it has a hard time loading the robot model. That might be the case again. Okay, so in Jupyter Notebook, this is the launch file you have to run. You have to put the sim argument to false. And if your network is working fine, this is what you're going to see at the end of it. If you see you can start planning now, looking around no, and replanning no, this means that you are good to go. And if you paid enough attention for what I explained in the previous section, this has nothing new right now for you. In Gazebo, you used to see how the robot moves around. Now you can see that in the real world. That's basically the difference. So let's check on the Dell again. Okay, it's taking its time. Go back to Jupyter. Okay, while it loads, let me show you what we're going to see. Okay, this is now a much more presentable model, a lot closer to what we have right now on the bench next to me. And again, we're going to use the planning tab. We're going to select start state, goal state. We're going to plan, and then we're going to execute. If it didn't start planning, it means that something is wrong with this, and we're going to just reset it and give it time so they can reload all the actions related to MoveIt, like move group. And after that's done, we can start planning. Now, having a not very decent connection is going to, I'm not going to say drastic, very critical problems, but it might slow stuff down. For example, later on that we're going to play the tic-tac-toe with the robot, you might get delays between sending one signal to the robot and the next signal that you're going to send to it. And instead of robot going from one place to the other, it might spend like 2 seconds and then go to the next position and orientation that we want it to go to. And problems like that might be in order. So, okay, it's nearly towards the end, but talking from experience, it's not going to work because of this error line here. So we're just going to reset it. Don't worry about anything. Again, we're just going to plan it to see how it's going to move from one pose to another. Let me open the graphical tools so that I can use the reset button. Okay. Expand this. Right, this is the robot as I left it right now. Planning, current. And right now, if you select this tab, you will see some predefined poses. Like start is, if I update this, is fully standing up. Rest 2 is something that we use a lot. It robot takes a bow, basically. If I plan this, okay, it won't let me. That's why I have to. So don't worry about anything. See if it did. Okay, it's resetting. Don't worry about the yellow warnings. Just RVs restarting itself. After understanding these parts, when we get to playing tic-tac-toe, it's not going to have any surprises for you. We had talked about how we sent the signals to the robot and how it's going to react receiving that signal. And let's talk about some unexpected occurrences while that happens. Sometimes, again, because of a bad connection, you might experience delays, lags. That is one of the unexpected occurrence. Sorry, and kinematic solver sometimes gets glitches. So by that I mean if you are in a state like this and you just want the robot to move slightly to the right, to just have this orientation but in a different position, you would think that the robot should move in a very simple manner, just this base moves and you're there. But sometimes, again, kinematic solver calculates this path for the robot so that it can go crazy before getting to that goal. So instead of just doing a simple movement, you will see movement in a lot of joints. It's like as if it's gone crazy. It just goes up, do different revolutions, and then just comes and not even accurately goes to the goal, towards the goal. Now, that is a rare occurrence, but I'm just letting you know so that there won't be any surprises later on as we proceed. And for playing the tic-tac-toe here, um, sometimes because of maybe not um, tuning the motors as well as they should be tuned, or using ductile materials instead of brittle materials. Uh, Grabbing one piece and placing it in the desired cell might not be very accurate. So something like this might happen. The piece can stand up like this to the side, to the edge of the cell. That is also something that we might see today. Hopefully not. Okay, let's check the shells again. Okay, I think we're good. Okay, let's update the current and let the robot stand up. Plan. Okay. Oh, oh, I did not update this. Okay. Plan now. And I'm going to press execute, and then immediately I'm going to show you the robot. Stood up. Now let's make the robot take a bow. Press 2, update, plan, and execute. Okay, so that was the explanation behind how you can interact with the robot through ROS Development Studio. Now that you know how this entire thing works, let's just play some tic-tac-toe. Um, this we don't want. Okay, we can use this one. But keep that in mind that this previous launch file should be running before you before you start playing tic-tac-toe. Sorry. So we have a package named tic-tac-toe, and we're just gonna ROS run it. We don't have a launch file for it. Just type ROS run tic-tac-toe tic-tac-toe1.py. So when I run this, there's a sequence of events that the robot has to go through. It's going to go to the initial state of it, open the gripper if it's closed, pick the first piece, come up, and go to the first starting point. Somewhere very close to this position and orientation. And then it waits for my command. We first initialize the cell 1, 2, 3, 4, 5, 6, and 7, 8, 9. We first initialize the board with this fifth cell as the center of it. And because it's symmetrical for around X and Y axes, there are no problems with identifying other cells because the increment from one cell to another, the difference in X's and Y's are the same. Same goes for the tray. We initialize it by the first cell, and we just add to the y-axis y element of xy coordinates that defines them, 1 through 5. So that's it. The robot picks one up, comes back, waits for your command, and immediately after placement of the piece, goes to the next one and waits for the command. So let's play. Okay. Okay, initial position, gripper is open, so pick the first one. Okay, come back and wait for my signal. Okay, let's go place one in the center, which is cell number 5. And X, Y, and Z's that you see here are X, Y, and Z of the cells that the end effector should hover there. And the X, Y, Z W, which indicates the quaternion, is pretty much the same for each and every one of them, because the gripper should always point down for gripping and placing. So we really didn't have to indicate that in our code. So if you don't mind, let's put 1 here, 5, and then 9, see what we're getting. Okay. I mean, I can also play, but I think you trust me enough to know that I can't play tic-tac-toe. So let's just focus on the robot. Okay, this is 9, so let's do 9 now. Now we're on the same track, let's do an X. So let's put the next one in 3, and the next one in 7. And while the robot is doing that, you can see it jump from one pose to another pose in the RViz environment. Each time it updates, you will see this phantom of a robot trying to get to the next goal. So this is the goal it currently is at, and this is the robot trying to get there. So, okay, we wanted to do it at 3, the other shell. Perfect. The last piece, we're going to do it. We're going to put it at 7. Yeah, kind of dropped it on this one. Probably it's tired. Oh, obviously. Okay, so that was a demo on Clarkson University's Open Manipulator. Hope you guys enjoyed it. Thank you so much for joining us again. And again, for the next steps of this project, it's full of potential, honestly. And this is not the pinnacle of our research, just to play tic-tac-toe with a robot. We are also working on an mobile robot project that maybe this robot will get mounted on, so that we can do other cool stuff with it. And again, possibilities are endless with this platform that we have over here. So on behalf of Clarkson University's robotics team, Dr. James Carroll, Dr. Ajay Sonar, Matthew Halterman, Jake Schechter, and yours truly, I thank you again for your attention and hope great success for your future endeavors. Thank you again. Have a great day.